identified for us this need to prevent, in the electric vehicle example, thermal runaway. And the task that we were given was to develop a material that was able to withstand 1200 centigrade, which would be the situation where a thermal runaway was occurring. And we began to work on this approximately a year and a half ago. I presented this material at the WE conference in Stuttgart, and we've continued to work on it. And so this is the first generation material that I'm presenting today, but the slides will provide a very clear explanation of just exactly how the material functions in thermal runaway conditions. Again, the development of material is based on, as Bob's talked about, the importance of safety in the vehicle. And as we say, the standards are continually evolving, even for this material, as the desire for protecting vehicle occupants from a thermal runaway event continue to increase. And so the development of the material is, as I said, can be used in anywhere that you're needing to block a fire. And so the material that we've developed is able to withstand 1200 centigrade direct oxyacetylene flame contact. I'll show you a video of that. The material is able to withstand and has been tested actually as high as 1400 centigrade, but realistically materials of either 0.8 millimeter or 2 millimeter have been tested both to our internal test procedure, which you'll see here, as well as to UL 2596, which I know others are familiar with. So the two grades that we have available currently are tailored to the UL specification, in which you have the test sample exposed to both the torch and then secondarily to blasting with aluminum oxide. And the Tektrasil material torch and grit grade has been tested to 2596 and has, and I'll use the term, qualified for the next phase of that testing, which is the BETR, or battery enclosure thermal runaway test, which is a much more difficult test because you're actually igniting cells in the battery, allowing the runaway to actually happen. The key properties of Tektrasil is that prior to a thermal event, the material maintains its elastomeric or viscoelastic properties. So it's able to seal, it's able to absorb vibration if it's a damper, or isolate if it's an isolator. And so you have the advantage of the material being able to have, I'll use the term, dual function. And in actual fact, the function in a thermal runaway is one you really don't want to have to deal with, but when it does happen, this material will transition from being elastomeric to being a barrier to that 1200 centigrade flame. The key properties, as I note in this slide, are can be achieved at as low as 0.8 millimeter, and one of the most important things that we have established for this material is that at the point the material begins the transition from an elastomer to fundamentally a ceramic, the material's thermal conductivity drops orders of magnitude, which again you'll see in data here. The two different grades that are available, as you can see from this data, and we have data sheets that are available at our booth, have durometers or hardnesses in the range of 73 to 75. There are softer and harder grades available. The tensile strengths are running in the 3.7 to 5.5 MPa, but more importantly, the material has useful elongation and the ability to exert sealing force, as I say, prior to a thermal runaway event. The material is resistant to compression set or loss of sealing force. In this case, this is testing that was conducted at 177 centigrade. And this is a measure of the thermal stability of the material. And the material also has good electrical properties as measured by its volume resistivity. The heat resistance of the material, and this is one of the unique properties of the material, is, and we've had some customers who have taken our testing at 1200 centigrade and concluded that if it's good at 1200, it's also good at 600, and that is not the case. The upper temperature limit of the material prior to the thermal runaway event would be the auto ignition temperature of the material, which would be 450 centigrade. So the important thing here is that the material should not be used outside of the scope of 150 to 175 centigrade, with excursions to 200 centigrade in terms of its resistance to heat. The dielectric strength of the material is for the Tektrasil T is 12, and the T&G grade is 10.6. Low temperature properties, we've tested the TR10, which is the temperature retraction of the material, which is the onset of crystallization, and it's minus 40 centigrade. The material prior to a thermal runaway event has a thermal conductivity of 0.80 watts per meter Kelvin. So it also, in a sealing application, is able to dissipate heat. Certainly not at the rates of the graphene products that we've heard about here today. Those are in a completely different class of materials than the Tektrasil material. The other properties that we have tested have been the flammability of the material, which we've tested according to UL 94, and the material is rated as V0 or V0, which means that after removal of the Bunsen burner from the test specimen, the material self-extinguishes within 10 seconds. This material actually extinguishes immediately based on the chemistry in the material. So I would like to show, and this should click on. So what you're looking at in this slide is the top and bottom of the test fixture. We have mechanically retained the Tektrasil sheet, and underneath there's a 1200 centigrade continuous flame. While we are running this test, as you can see here, we are also measuring the top side temperature, and what you can see is that up to a point the temperature increases, the material converts from elastomeric to ceramic, and the temperature drops. But if you look at the y-axis on these graphs, you can see that the material at no point in time on the top side rises above the auto ignition temperature of the material. This is of great significance to our customers, but you can see from the video. So we have run this test, as I say, at thicknesses as low as 0.8 millimeters. And what you can see on the top side as a result of our having mechanically retained the samples is that the material is only able to expand in the z-axis. It does not expand, or not allowed to expand either in the x or y. And so this is part of our test protocol, which we call mechanical retention. We're also now doing weighted retention where we do allow it to expand. And in that case, the buckling you see in the videos doesn't occur. So we have also tested as high as 1400 centigrade for 30 minutes. That was done at 2 millimeters. But from my own standpoint, this is would be the absolute upper limit of the material. And again, you can see the oxyacetylene flame come up on the hot side. You can see the behavior of the material on the top. There is zero burn through of this material. And that is Tektrasil.